So we just derived this following expression for the amplitude of force response given some external forcing, right? So we have some external force, which is perfectly periodic, sine omega t times F naught for a system with no damping. And x of t in response to this forced oscillation, periodic external force, has this amplitude A, for which we derive this formula A equals F naught divided by K, 1 minus omega divided by omega n whole squared. Okay? Now, what can we infer from this formula? So meaning of this formula. So let's call this equation 3 or equation 4. So let's call this equation 3. And let's call this equation number 4. So equation 4, intuition, let's say. So let's actually divide F naught divided by K by A, or we can leave it on the right hand side, doesn't matter. So let's just leave it as it is, F naught divided by K on the numerator, and then 1 minus omega over omega n whole square on the denominator. Okay. So what, by the way, is F naught by K? F naught by K is what would be called the static deflection. Okay. F naught by K equals delta ST for a given constant force, F naught, on the spring of stiffness K. In other words, if you pull on the spring with a constant force F naught, it will deflect or it will deform by F naught divided by K. So that's the meaning of F naught divided by K. Okay, so let's sort of keep that aside. So A is this quantity, F naught divided by K divided by this quantity. Let's plot this. Let's plot actually just the 1 over 1 minus omega divided by omega n whole square. Okay, let's plot this curve. Okay, because this itself is just a constant. Okay, let's plot this curve as a function of omega. Actually, let's plot it as a function of omega divided by omega n. Okay, so when omega divided by omega n equals, so let's actually write a table down. Okay, when omega over omega n equals 0, in other words, when omega equals 0, this quantity is going to be equal to 1, right? So when you plug this equal to 0, you plug this equal to 0, 1 over 1 is 0. So that's one value. And then we have when omega over omega 1 is infinity, in other words, omega is very, very large, then we say this is 1 divided by essentially, well, this is infinity, and then you can square it and basically have minus infinity. Okay, so maybe it's better to actually plot the absolute value of this. So this quantity is actually 0. And then the third quantity we want to say is omega over omega n is equal to 1, the value of that. And when omega over omega n equals 1, so this quantity equals 1, 1 minus 1 becomes 0, 1 over 0 becomes infinity. Okay, so we have this table of values for this quantity which is the sort of the key quantity in this amplitude expression. There's some constant times this quantity. Okay, so let's now plot this using these three expressions, these three values. So when, let me use a different color perhaps. So when omega over omega n is 0, so that's 0, this is equal to 1, so that's this thing. And then when omega over omega n equals 1, this is 1, this actually goes to infinity. So you have a curve that sort of goes to infinity here. And then when omega over omega n goes to infinity, in other words, very, very large, this quantity, it says the value is 0. So that's what that looks like, the curve. If you plot this expression in terms of omega over omega n, you have this relationship. Okay. Now, what does this relationship mean? It means that when you oscillate the system, so this is low frequency oscillation, low frequency forcing, low frequency or zero frequency forcing. This is high, very high frequency. So this is very low frequency, very high frequency forcing. And this is what would be called resonance. Okay, when omega over omega n equals 1 or omega equals omega n. When omega equals omega n, what that means is that the forcing frequency is equal to the natural frequency. That's omega equals omega n, or omega over omega n equals 1. And the idea is that when that's the case, this quantity, which is basically the response amplitude, how much the system moves in response to the forcing, the response amplitude goes to infinity. Okay, so what this means is that at resonance, in other words, when the forcing frequency matches the natural frequency, you get an amplitude of motion that is very, very large, or in this mathematical limit, actually infinity. When you force it with very, very low frequency, or basically almost zero frequency, which is essentially applying a constant force, it says that A equals essentially equal to the static deflection or the static deformation, which makes sense because you're essentially applying a constant force. A zero frequency force is a constant force. So you're just applying F naught as a constant force. And of course, the deflection or the deformation is going to be F naught over K. That makes sense. And then when you have very large frequency, omega over omega n equals infinity, in other words, the forcing frequency is much, much, much larger than the natural frequency, then it says the amplitude goes to 0. And that's this limit. So this is the low frequency limit. This is the high frequency limit. So high frequency is not actually a bad thing in this case from the perspective of amplitude of vibration. Low frequency is also not a bad thing necessarily, it's relatively small. But this intermediate frequency, where the natural frequency matches the forcing frequency, is what's called resonance, and you get incredibly large vibration oscillation. Okay. Now this is in the absence of damping, which is why the amplitude goes to infinity. But in the presence of damping, the amplitude does not go to infinity, it remains finite. And greater the damping, smaller the amplitude, even at resonance. So damping is a way you can actually reduce the resonant, the maximum amplitude at resonance. Also, when you're designing a machine, you want to understand what are the external forcing functions that act on the machine, or what are the forces that the machine itself produces. And we want to make sure that the natural frequencies are not very close to the operating frequencies of the machine or the typical external forces that the machine experiences. So that's very important. because we want to usually avoid resonance to avoid catastrophic failures. Maybe in some situations, you might actually want large amplitudes and you might actually want to take advantage of resonance. That also happens. Okay, so that's it for this lecture.